All right, welcome back to the deep dive. Today we're taking a look at something pretty interesting, a new paper that asks a really, really important question, especially for robotics, right?
Okay.
The paper is called Can We Detect Failures Without Failure Data? Uncertainty-Aware Runtime Failure Detection for Imitation Learning Policies. So from the title, you can kind of get what this is about, right? If we have robots that we're training with these, more advanced machine learning methods, how can we tell if they're about to make a mistake or they are making a mistake if all we've shown them is how to succeed? And this paper from Toyota Research Institute and woven by Toyota is offering kind of a new take on how to approach that very question.
Yeah, it's becoming more and more of a fundamental question as we move into, more sophisticated robotic systems operating in real-world scenarios where they have to deal with so much uncertainty and unexpected situations.
Yeah, I mean, you think about like a robot working in a hospital, right? Or navigating a warehouse. Like the possibilities for something to go wrong are kind of endless.
Yeah.
So you can't really pre-program a response for everything.
Right.
And that's the core problem they're going after, right? Most of the ways we currently detect when a robot is malfunctioning relies on us having seen those malfunctions before, right?
Right.
Like we need data on how robots fail to train systems to detect those failures. And they're basically saying like, hey, that's a pretty big limitation. You can't just collect data on every possible way a robot could fail at, assembling a piece of furniture.
Right. You'd have to make the robot fail in every single way imaginable. It's kind of an impossible task.
Exactly. And not only that, but even if you did that right, like how do you know you've covered everything? There might be some really weird edge case that you just haven't seen before. So what they've done is come up with the system called FailDetect. And the really neat part about it is it's designed to detect failures using only the data from successful robot demonstrations. So it kind of flips the problem on its head. Instead of saying like, okay, how do we define what failure is? They're saying, how do we know what success is? And how do we know when we're deviating from that?
Right.
So it's more like anomaly detection than trying to explicitly, classify all the failures.
Right. I mean, it's a really clever way of looking at it because you're absolutely right. Trying to define failure is like, it's kind of a bottomless pit. But looking at success, like, how can we deviate from what we already know works? That's a much more constrained problem.
Yeah. And their approach works in two main stages. So the first stage is all about taking all of the complex information that a robot takes in and puts out, things like what its cameras see, the angles of its joints, the actions it's planning to take. They kind of condense all that down into a single number, right? A score. And that score is designed to be very sensitive to when something might be going wrong or is about to go wrong. And they also try to bake in some measure of how certain or uncertain the robot is about what it's doing. And they explore a bunch of different ways to calculate these scores. Some of them use machine learning models. Some of them are like more direct calculations after the robot has taken some actions. So there's a bunch of different kind of techniques that they use to condense all this high dimensional information down to a single score.
And then that second stage is really about using that score to make the decision. Has a failure occurred or not?
Oh.
And the key here is how they determine the threshold, the point at which that score indicates a likely failure. They use this statistical technique called conformal prediction.
Conformal prediction. I'm not familiar with that.
Yeah, so conformal prediction, it sounds complicated, but I think maybe a decent analogy might be, let's say you're tracking like a basketball player, right? And you're tracking all their shots in practice, right? And so you can kind of get an idea of like, what's a typical performance for them, right?
Yeah.
And you build up this kind of like confidence range, and conformal prediction allows you to do that in a way that, has some like statistical guarantees on it.
Right.
So you can say like, like 95% confidence, we think their shots are going to fall, within this range.
Right.
And then let's say in the middle of a game, right? Like all of a sudden they take a shot and it's like way outside of this expected range. Well, you have good reason to believe that something's up, right? Maybe they're injured, maybe, something's off, right? And so FailDetect kind of does something similar with the robot's performance score, right?
Yeah.
It builds this kind of like time varying boundary,
Right.
Based on what it's seen during successful training runs.
Right.
And if the score, during a new task all of a sudden goes outside that boundary, then it flags that as a potential failure. And that time varying aspect is really, really important, right? Because what's normal for the robot at one point in a task might be totally different from what's normal at another point.
Okay, that makes sense.
Yeah.
So, to kind of put this work in context and really understand what led to this paper, they start off by talking about, the really impressive progress we've seen in robotic manipulation thanks to imitation learning,
Right.
and particularly with these new generative models, think diffusion models, flow-based models. They can learn really intricate skills just by watching demonstrations, which is super cool.
Right.
But one of the problems is that they can sometimes generate unexpected or even noisy actions, especially when they come across a situation that they haven't seen before, right?
Right. These models are really good at picking up patterns, but if they're faced with something that's outside those patterns, something we call an out of distribution scenario, their performance can really degrade, and that's where the failures start to creep in.
Exactly. And as the paper points out, detecting those failures in those situations can be quite tricky because, first of all, the data robots deal with is really high dimensional.
Oh yeah.
It's not just a couple of numbers. And second of all, in imitation learning, you don't always have a nice, clear-cut definition of failure like you might have in a more traditional reinforcement learning setting where you have like a reward function that tells you exactly what you should and shouldn't be doing.
Right. Right. Exactly.
So before they even get into their method, they take a look at what others have done in this space. They do a really good job of reviewing all these different techniques for out-of-distribution detection, which is a pretty core idea behind what they're trying to do. And there's a lot of different ideas in that field, right? You've got like ensemble methods where you use multiple machine learning models to try and estimate how certain or uncertain the system is, but that can be really computationally expensive. You've got classification-based methods, but they usually require you to have examples of failures to be able to train the classifier to recognize failures, which is kind of the thing this paper's trying to get around, right?
Right.
So they can't really use those. And then you have density-based methods, which try to kind of learn the shape of the normal data, but those can be difficult to use in very complex, high-dimensional situations. And they also mention some other things like one-class discriminators and evidential deep learning and distance-based approaches. So there's a whole kind of toolkit of methods that people have explored for detecting these kind of unexpected situations.
Absolutely. And even within the robotics community itself, there's been a lot of work specifically on this problem of failure detection. But as you said, like a lot of that work either still requires having failure data or it isn't really designed for these newer imitation learning techniques that are using these generative models.
Right.
And the paper actually points out some pretty interesting approaches, like, for example, some work that's using insights from large language models to try and understand when something's going wrong, or even work that analyzes the errors when a model is trying to reconstruct its observations as a way of detecting failures.
Okay, interesting.
But I think the key takeaway from their kind of survey of existing work is that there's still a real need for a solid, reliable way to detect failures in these advanced robotic systems when we don't have, this nice, neat catalog of past mistakes to learn from.
Right.
And they make a really good point of contrasting their work with a recent state-of-the-art method called STACK. Right. And this ASTAC method also tries to tackle this problem of detecting failures without actually having failure data. And it does this by looking at how consistent the robot's predicted actions are over time. So it kind of assumes that if the robot starts doing things that are very different from what it's done in the past, that might be an indicator that something's wrong.
Makes sense.
Yeah, and it actually also uses conformal prediction.
Okay.
But the authors of this new paper argue that FailDetect improves on STACK in a couple of important ways. First, by using these learned scalar scores that we've been talking about. And second, and this is actually really crucial, by using a conformal prediction threshold that changes over time rather than staying fixed.
Right.
And that time varying threshold is a really big deal, as we've been talking about, right? Because a fixed threshold, well, it might be too sensitive at certain points in a task and end up raising a bunch of false alarms, or it might not be sensitive enough at other points and completely miss a real failure. So by allowing the threshold to kind of adapt based on what's, expected variability in the robot's behavior throughout the task, you end up with much more accurate failure detection.
Yeah, that makes sense. That makes a lot of sense. So getting into a little bit of the nitty-gritty here of how they actually approach this problem in their problem formulation section, they start by laying out kind of the key components here. You've got the generator, which is the AI model that decides what action the robot should take based on what it's observing. And then you've got the trajectory, which is basically the sequence of those observations and actions over time.
Right.
And they define the failure detection problem as basically designing a function that looks at that trajectory and makes a decision. Is this a failure, yes or no?
Right, exactly. And then their FailDetect framework, as we've discussed, has those two key steps. First, training a model to produce that scalar score that we've been talking about, using only the data from successful robot runs. And then second, using conformal prediction to create that dynamically adjusting threshold for that score. Right. And if the score goes above the threshold, boom, failure is flagged.
Okay, so let's talk a little bit about how they actually designed those scores, right? Because that was kind of the heart of their first stage.
Yeah.
And they had some pretty key requirements for these scores, right? First of all, they couldn't rely on any failure data for training.
Right.
They had to be lightweight enough computationally to be able to run really quickly on a robot in a real-time setting. And third, they needed to be actually good at telling the difference between when a robot's operating successfully and when it's not, right? Like they actually had to be informative.
Right.
So they explored several different kind of categories of potential scores. One was based on this idea of learned data density, which is basically the idea that if the robot encounters a situation that's very different from what it experienced during those successful training runs, that might be a sign that something's wrong. And they looked at an existing method for doing this called LOPO, which tries to kind of directly model the probability distribution of those successful observations. But they also introduced their own kind of novel approach, which they called logPizio.
Right.
logPizio. And it seemed like that was a really key contribution of their paper.
Yeah, absolutely.
So how does that one work? What's kind of the insight behind it?
Yeah, so logPizio uses a similar kind of model for estimating data density.
Right.
But instead of directly evaluating the likelihood in the space of the robot's observations, which can be, we've talked about this could be really, really complex, right?
Yeah.
It does this kind of clever trick where it evaluates the likelihood in a transformed, kind of simpler noise space.
Noise space.
Right. And the basic idea there is that it might actually be easier to spot anomalies, things that don't fit the pattern of success in this simpler noise space than it is in the original super high-dimensional observation space. And the researchers actually hypothesized that logPizio would perform better because it kind of avoids some of the pitfalls that come with trying to directly estimate the density in that original complex observation space. And actually, their experimental results did kind of support this idea, showing that logPizio often did a better job of distinguishing success from failure.
Okay, that makes sense. So it's almost like they found a way to simplify the problem by looking at it from a slightly different angle, right?
Exactly.
And that simplification actually made it easier to spot the problems.
Yeah, exactly.
Okay, so that's really cool.
Yeah, it's a really clever twist on the problem.
So they also looked at what they called second-order methods, which basically tried to learn the parameters of some sort of statistical distributions that could capture different kinds of uncertainty in the robot's behavior. And then they looked at one-class discriminators, which learn a boundary around the successful data without trying to explicitly model the full probability distribution.
Right.
And some examples of that were like R&D, which learns a mapping that should be consistent for successful data, but deviate when things are going wrong.
Right.
And CFM, which basically looks at how curved the robot's trajectory is in some sort of learned model representation, with the idea that higher curvature might indicate that something unusual is happening.
Right.
So for R&D, the idea there is that if you train it to match like a random target, right?
Yeah.
If the robot encounters something new or weird, its actions are going to look really different from that target that it was trained to match, right?
Right.
Okay, that makes sense.
Exactly.
And then finally, they also looked at what they call post hoc metrics. These are things you can just calculate directly from the robot's behavior after it's done its thing. You don't need to do any extra training to detect the failure itself. So things like Spark, which basically measures how smooth the robot's actions are. Like if it starts moving all jerky or erratically, that might be a sign of a problem. And of course, the stack baseline that we mentioned earlier, which looks at how surprising the robot's predicted actions are compared to its past successful actions. They also adapted this existing out-of-distribution detection technique called PCA k-means as another post hoc baseline to compare against.
Right.
And then kind of the second really critical part of this whole FailDetect framework is how they design that sequential failure detection threshold using conformal prediction, right?
Yeah.
And as you explained earlier, they use this technique called functional conformal prediction to create this time-varying band around the expected scores during successful runs.
Right.
And that band has this nice statistical guarantee. It says that any score generated from a genuinely successful run should fall within this band with, like, some predefined probability, right?
Right, exactly.
Like 95% or something like that. And then they use the upper edge of that band as the threshold. So if the score ever goes above that edge, it gets flagged as a potential failure.
Right.
And what's really neat about that is how it changes over time, right?
Oh, yeah.
So you can think about it like if you've got a robot that's picking up a very delicate object, maybe the normal variability in its sensor readings is going to be pretty small, right?
Right.
But then if it has to start moving that object quickly, maybe the expected variability should actually increase.
Right.
And the conformal prediction framework lets that failure detection threshold widen or narrow accordingly to kind of match those changing expectations about how the robot should be behaving throughout the task.
Yeah, it's a really elegant way to handle those different phases of a complex task.
So to really put this FailDetect framework through its paces, they ran a bunch of experiments in both simulations and on real robots. So for the simulations, they used this benchmark called RoboMimic, which has a variety of manipulation tasks like moving a square around, transporting objects, hanging a tool, things like that.
Right.
And then they also did experiments on real robots using a Franca Emica Panda arm.
Okay.
And they gave it two kind of challenging tasks, folding a red towel and cleaning up a simulated spill. And they deliberately created these out-of-distribution scenarios to see how well their method would handle these unexpected situations.
Right.
So, for example, in the simulations, they introduce like a sudden bump to the camera to kind of throw the robot off a little bit.
Okay.
And then on the real robot, they would like use a towel that was a different color than the red towel that it was trained on.
Okay.
Or they would like really crumple up the towel to make it harder to fold. So they were trying to really stress test the system to see how robust it was. And in all of their experiments, they compared the performance of their FailDetect framework using all those different scalar score methods that we talked about against these existing methods like stack and PCAK means.
Right.
And what did they find? What were the results?
Well, the results are really, really encouraging.
Yeah.
So first and foremost, they found that FailDetect did a really great job of actually detecting failures in both the simulations and the real world experiments.
Okay.
And crucially, it did all of this without ever having seen an example of a failure during its training phase.
Right, right.
Which is pretty remarkable.
That's really cool.
And it suggests that their kind of core idea, right, this idea of framing failure detection as basically identifying when you're deviating from this learned pattern of success is actually a really solid strategy.
Yeah, that's really neat.
Yeah, so to put some numbers on it, they found that the learned score candidates within FailDetect achieved an average best accuracy of around 75% in both the simulations and the real world experiments, which is, it's a really promising result. And importantly, they also showed that their system could detect these failures pretty quickly, often intervening before the robot could even complete the task incorrectly.
Wow.
Yeah, so it's not just about, catching failures, it's about catching them early enough to actually do something about it.
Right, because if you can catch them early, maybe you can prevent them from happening in the first place.
Exactly. And that underscores a really important takeaway from this work, which is that letting the data kind of define what normal behavior looks like through these learned representations that we've been talking about seems to be much more effective for detecting anomalies than relying on our kind of preconceived notions of what should be considered a problem.
Yeah, I mean, it's really counterintuitive in a way, right? Like you think, oh, we can just like program in all the things that look like a failure and then we can detect failures. But it turns out that actually letting the data speak for itself is a lot more powerful.
Exactly.
That's really cool.
Ken, I think maybe one of the biggest takeaways from the paper is that they saw this really clear advantage to using those learned scalar scores compared to the more traditional post hoc metrics.
Right.
So they found that the scores that were actually learned by machine learning models, particularly their novel logPizio method and that R&D approach that we talked about, consistently outperformed the scores that were just directly calculated from the robot's behavior.
Interesting.
And logPizio in particular, it seemed to be the most consistently high performing across all the different tasks and conditions that they tested.
Wow.
So that kind of points to the power of really letting the data itself guide the system in terms of learning what constitutes normal or successful behavior.
So is that like a suggestion that in the future, maybe we should focus more on those kinds of data-driven methods as opposed to these more hand-engineered metrics.
Yeah, I think the evidence from this paper certainly points in that direction. That these learned representations seem to be much better at capturing these kind of subtle cues that something might be going wrong compared to these more manually defined metrics, like how smoothly the robot's moving or how statistically consistent its predicted actions are.
Okay.
Yeah.
And they also found that these learned methods generally led to faster detection of failures as well, right?
Yeah, absolutely. In fact, they found that while the stack baseline could sometimes achieve, decent accuracy, it often took a lot longer to flag a failure, sometimes even longer than the average time it took for a successful run, which obviously wouldn't be very helpful if you're trying to intervene in real time.
Yeah, you don't want to wait until after the failure has happened to detect it.
Exactly.
So speed is definitely important.
Yeah.
And it was really interesting to see that their logPizio score was so much faster to compute than Stack, especially because Stack relies on doing all this sampling and comparing distribution.
Right. It's a much more computationally expensive approach.
Yeah, so that's a big win for logPizio, right? Because not only is it more accurate, it's also faster, which means it's more practical for real world use.
Absolutely. And, it's not just about the raw numbers. One thing that I thought was really cool was that the researchers actually provided some qualitative examples showing that when FailDetect flagged a failure, it often corresponded to events that a human observer would immediately recognize as a problem.
Oh, interesting. Like what kind of events?
So things like, the robot's gripper losing its grip on an object, or, maybe the robot dropping something that it was holding,
Yeah.
or even like failing to execute a key step in the task.
Okay.
And those spikes in their learned failure scores, they actually lined up with these kind of meaningful physical events.
That's really cool because it kind of shows that the system is learning something that's actually grounded in the physical reality of the situation.
Exactly.
It's not just some arbitrary mathematical thing. It's actually reflecting what's happening in the real world.
Absolutely.
And that's really important for building trust in these kinds of systems, right?
Oh, yeah.
Because if a robot says, hey, I think there's a failure happening, and then a human looks at it and says, yeah, I can see exactly what went wrong, that gives us a lot more confidence that the system is actually doing something useful.
Absolutely. And, one other interesting thing that they found in their experiments on the real robot was that while a single failure detection threshold calibrated on successful runs in, kind of the standard conditions worked really well in the simulated environment, on the real robot, they actually found that using thresholds that were calibrated on slightly different but still successful out-of-distribution runs actually improved the performance.
Oh, interesting. So they're almost like tailoring the threshold to the specific environment and the specific kinds of variations that they might expect to see.
Exactly. So, for example, they found that when they calibrated the thresholds using runs with the crumpled towel, the system was better at detecting failures when it encountered that crumpled towel during the actual test.
Right.
And I think that kind of highlights, this idea that in the real world, our definition of what constitutes normal might need to be a little bit more flexible and context dependent.
Yeah, I mean, that makes a lot of sense, right? Because the real world is always going to throw you curveballs that you didn't anticipate.
Absolutely.
So being able to adapt to those variations is really important.
Yeah.
Of course, no paper is perfect, and the authors do a good job of highlighting some of the limitations of their current work. One thing they point out is that sometimes their learned scores seem to focus more on the kind of basic robot joint states and didn't really fully leverage the richer information available in the visual data. They also mentioned that their current scoring methods don't explicitly take into account long sequences of actions and observations over time. And they also only used visual and robot state data, suggesting that maybe incorporating other sensory information like sound or touch could potentially lead to even better failure detection.
Yeah, and I think those limitations are really valuable because they kind of point towards some very clear directions for future research. Like, how can we design these learned models to really take advantage of all the rich visual information that robots are perceiving? And how can we incorporate a longer memory of the robot's past behavior into these failure detection mechanisms?
Yeah, those are great questions.
Yeah.
So just to wrap up our discussion of the paper itself, they present this really promising two-stage framework, right? FailDetect, for detecting failures in these robots that learn by watching demonstrations. And the really key innovation is its ability to do this without ever needing to see examples of failures during training.
Right.
They use these informative scalar scores, right? They learn them from successful runs.
Yeah.
They use this really cool time-varying conformal prediction to set adaptive thresholds, and they show really robust and fast failure detection across a range of tasks,
Yeah.
both in simulation and the real world. And I think that the consistent performance of their novel logPizio score is a really big contribution to the field, highlighting the power of these learned density estimation techniques for this kind of problem.
Absolutely.
And overall, I think this work represents a really important step towards making these sophisticated robots much safer and more reliable for use in these complex, unpredictable environments.
Absolutely.
And as always, if you're interested in getting into the weeds a little bit more, a link to the full paper is available down below.
Yeah.
But now let's move on to something a little bit more fun, right?
Okay.
Our novel notions segment, where we like to kind of brainstorm about some, potentially groundbreaking, but maybe a little bit outlandish future research directions inspired by this work.
Yeah, I like to think of it as, taking the paper as a jumping off point and then seeing how far we can kind of stretch our imagination.
Yeah, exactly. So what kind of crazy ideas has this paper sparked for you?
Well, I think building on their success and learning these scalar scores that correlate with failure, there's a really interesting opportunity to move beyond just detecting failures after they've already started to happen and actually start predicting them before they occur.
Oh, that's interesting. Predicting failures before they even happen?
Yeah.
Like, how would you even go about doing that?
Well, the paper kind of hints at this possibility, right? They show that these scores often show certain patterns or trends leading up to an observable failure.
Okay.
So my first novel notion here is what I'm calling proactive failure prediction through latent space trajectory analysis. And the idea here is to actually train a temporal model, maybe something like a recurrent neural network or a transformer, to analyze the sequence of these learned failure scores over time, as well as the kind of underlying representations within the generative policy that's guiding the robot's actions during those successful operations.
So the idea is to look for subtle changes or like increasing levels of uncertainty in those internal representations before the score actually crosses that detection threshold.
Exactly. So, imagine, for example, you have a robot arm and it's starting to lose its grip on an object.
Okay.
Right? The logPizio score might still be, within that safe range.
Right.
But the way that score is evolving over time, or the patterns in those underlying action decisions that the policy is making, might start to resemble patterns that were associated with past near misses, or even failures that we've simulated, even if those specific failures weren't part of the original training data.
Okay.
Right. So by kind of learning the dynamics of success, we could potentially identify when the robot is on a trajectory towards failure before it actually makes a mistake.
Yeah.
It's kind of like if you think about predictive maintenance for machinery,
Wait.
where we analyze trends in sensor readings to try and predict when a machine might break down.
Right.
This is kind of like applying that same idea to robot behavior.
That's really interesting. And what makes you think that this could actually work?
Well, I mean, the paper already shows that they can capture these deviations from successful behavior really effectively. So it seems like analyzing the temporal patterns of those deviations is a pretty logical next step.
Okay.
And we might even be able to borrow ideas from research on, early warning signs in complex systems or anomaly detection in time series data. There's a lot of work in those areas that could potentially be applicable here.
Yeah, and the potential impact of that is huge, right? If you can intervene earlier, you might be able to prevent damage to the robot, prevent damage to its surroundings, maybe allow the robot to replan its actions in a way that avoids the failure, or even like trigger a graceful stop before something really bad happens.
Exactly.
So you could have robots that not only detect mistakes, but actually learn to anticipate and actively avoid them, which is like a whole other level of intelligence.
Right.
I like it.
Yeah.
So how likely do you think this is to actually pan out as a research direction?
I think it's definitely worth exploring. I'd say the probability is probably medium. It would require developing some pretty robust methods for interpreting these complex temporal patterns and distinguishing between, just normal variations and genuine pre-failure signals. But I think it's a really exciting avenue to go down.
Okay. I like it. So that was your first crazy idea. What's your second one?
All right. So my second novel notion is a little bit more out there.
Okay.
It leans more towards kind of augmenting this purely statistical approach with some higher level reasoning. Right. So FailDetect is really good at spotting these statistical anomalies in the robot's behavior. But what about failures that might seem kind of sensible from a common sense perspective, even if the low-level actions themselves look, statistically normal?
Okay, I see what you're getting at.
So my second idea is what I'm calling incorporating common sense and environmental understanding for enhanced failure contextualization.